I need to bump up the volume a little bit. Okay, that's about right. All right. So getting back to what I was talking about, you might have noticed that this is, it doesn't look like Windows, 7. Definitely it doesn't look like Windows 8. If anything, it looks more like the older versions of Windows. So the question is, what is an operating system? What do you think is an operating system?
User interface?
Hmm?
User interface?
Is an interface? That's one part of an operating system that we know of. In the good old days, that's not even really considered a part of an operating system. Well, I guess you can say an operating system is one that is functioning, operating as in non-operating. But that's not what operating system means. Go ahead.
It controls the flow of information from the user to the...
It manages everything. It manages everything. So it's a coordination type of software. If I want to pick an analogy, an operating system is more like a government. Okay. Really, you have a lot of resources on one hand. What type of resources are we talking about? From chapter 1, you learned that inside the computer, inside the box here, there's a lot of resources. So what kind of resources are we talking about? CPU, and then graphics card, memory. How about the hard drive? How do we classify the hard drive as a resource? Mass store. Anything else? What about this? Input devices, output devices. So a computer has a lot of these resources, and can I only use a particular brand of mouse on any computer?
No.
What happens if I switch out my Logitech and plug in a Microsoft instead? Would it still work? It still work, okay? So a lot of resources to begin with, and with each type of resource, there's also a lot of alternatives. Okay, if you just think about printers, and you go to Office Max or go to Fry's, there are all kinds of printers that you can buy, all kinds of keyboards that you can buy. Okay, so the question is, okay, with all these resources and also the alternatives of the resources, how do you write an application that can make use or utilize these resources effectively? What kind of application are we talking about? What do you use the computer for? That's the question. What do you use a computer for? Let's not think about classes, because you guys do not really like boring and dry subjects. Let's think about gaming. Okay? So you're using your computer for gaming purposes. The question is, how can the game programmers or developers develop games more effectively? Okay, I give you two alternatives. One alternative, no operating system whatsoever. So the game developers will have to think about, okay, what kind of devices the gamer is going to use? How many controllers are there out there for playing games? A lot, right? What about keyboards, gaming keyboards? There's a lot of, there are some alternatives. What about graphics cards? Gamers like to use, the latest and greatest graphics cards, right? Do you think they all work the same way as far as the developer is concerned?
No.
At the lowest level?
Yes.
At the lowest level. Well, that's called the Vga Compatibility Mode, and you don't want to use that for gaming purposes. Why does someone, not necessarily you, spend $500 on the graphics card instead of 30?
Get 2 more frames per second.
We'll get some more frames per second, or the room is too cold and it needs to be heated up. The graphics card is a really good, nice heater. Okay?
Hey, mine only works at 40.
But from the game developer, the programmer's perspective, it is a big hassle to think about all 200 possible video cards that people can put into that system, and say, okay, if you're using this card, I'm going to have to write this back end of the software a little bit differently. If you're using this video card, I have to do it a little bit differently. What if after you release a game, NVIDIA decides to release a new chipset that works, even better than the old ones? but you kind of need to tweak the software to make use of the new features. The developer will have to go back and say, oh, okay, I'll add another video card to the game. Isn't that going to be a big hassle as far as the game developer is concerned, the person who's writing the games?
Get the writing support for DirectX.
But there's no operating system, and there's no DirectX in this case. Okay? So that's why we have an operating system. The operating system is here as a middle person so that the game developer never have to worry about or too much. He or she doesn't have to think about what kind of video card or how much RAM or what kind of mass store you're using with your computer, because when a game application, when a game program runs, it's just asking the operating system for resources. Okay, it's telling the operating system or the GUI or the graphical user interface of the operating system and say, I want to create an object here in 3D space. This is the texture and these are the lighting conditions. And leave it up to the operating system to communicate with the graphics card. Now, if you have a really smart and high-end graphics card, the graphics card can store that information and do all the rendering by itself. But if you're like me with a $30 graphics card, sometimes the processor has to help out in terms of rendering the graphics, what is on screen. What about the keyboard, the game controller, and stuff like that? Those are resources to the game as well. Okay? So the game developer just has to say, okay, when the game controller changes its position or changes when the button is clicked, let me know and I'll handle it. I know what to do with the trigger click on the game controller. But which brand of controller are we talking about? The game doesn't really care. In most cases, it doesn't care, okay, unless you have a really high-end one and the game supports it. Are there any questions about this conversation at this point? No questions? So the operating system is acting as a middle person because on one hand you have software that depends on the individual hardware. Those are what we call what? You get a new device to install in your system and Windows will say it's looking for what?
Drivers.
The driver, okay? So the driver is the only piece in the system that is hardware dependent. And who supplies the driver? The manufacturer or the vendor, whoever makes the chipset typically supplies the driver, but the brand that sells the product will kind of rebrand it, into their own name. Okay. What else do you think the operating system is useful for? Okay, let's say you have 8 gigs of RAM, which in my world is a lot of RAM. I live with 1 gig. I still live with only 1 gig for the most part. So let's say you have 8 gigs of RAM, and you're running, let's say, a few applications. You have a browser, word processor, a spreadsheet, maybe a game running in the background at the same time. So when your game says, I need some extra memory to store a few more frames, okay, how do you think that works out? Do you think the game program just goes to memory and go like, yeah, I like that chunk of memory right there, I'm going to take it?
Request it from operating system.
It has to request it from the operating system. Why can't your game just be efficient and just say, I'm going to grab that chunk of RAM?
May conflict with other programs.
Exactly. What if that chunk of RAM is being used by your browser? What if it's being used by your word processor, Microsoft Word, or the likes? Okay, so the operating system is really doing the job of a government, okay, doing all kinds of regulations, handling the allocation and deallocation of resources, and so on and so forth. So by the time you have to write an application, the application doesn't have to worry about that sort of stuff anymore. Okay, are there any questions at this point? So an operating system is really just a resource manager to make sure that resources are allocated and deallocated correctly, and applications cannot trash each other. In other words, one misbehaving application program cannot cause your entire system to crash. But there were days in the past when that can happen. Which operating system was the last one that still allowed one application to basically host your entire system? It's a Microsoft product.
Probably ME.
Hmm?
Probably ME.
ME was the last one, correct. And how well did it sell? There you go. That's the right answer. XP was the first consumer Microsoft Windows that has the NT kernel, which has much better protection, so that one application cannot cause the entire system to freeze up and crash.
Now every one of Microsoft's operating system has it.
Yep.
It's the N7.
And that's after many, many years that the processor supports that feature. The 386 processor was the first one that allows the operating system to protect applications from each other. When was the 386 processor released?
90.
I think it is, let me see. No, it's way before that. It's way before that because I was in my last year in the University of Hong Kong, and I graduated from there in '89. So 1989 was the first year that the 386 processor came out that has all the hardware features to implement a protective operating system. And when does XP come out? When did XP come out? Come out? 2003? Was it 2003? Yeah, it's about 2003 because NT4 was was still running in 2000.
It was in beta testing in 2001.
Yep. So it's off by how many years? 89 to 2004 to 2003. 14 years or so. Yep. Hardware was already available in 1989, and software finally caught up in 2003 or 2004 for consumers. Okay, the NT kernel was available already for commercial purposes. All right. Well, that's what, in a nutshell, that's what an operating system is. And I'm running Linux here, which has a slightly different user interface, but more importantly, underneath it is entirely different. In other words, it talks a completely different language. And as a government, okay, this is an entirely different type of government. So we are talking about governments that have the basic same features, kind of like comparing the U.S. government to, say, the British government. Okay, they have the same sharing of power from 3 different divisions. Both have two houses. Okay, in the United States we have the Congress and also the Senate, but in the British system they have the House of Commons and the House of what? I can't remember the name. Representatives?
It's a House of Commons and a House of Emergency.
Yeah, but they have 2 houses, just like the United States. And they have legislative branch, the judicial branch, and also the executive branch. It's just named differently, okay? But things are not exactly compatible, right? They don't use the same terms, and certain regulations are slightly different. You go to a slightly different department for certain things, when you need to utilize resources, when you ask for resources from the government. It's the same thing here with an operating system. An application designed for Windows only know how to ask for resources, from an operating system like Windows. Maybe different versions of Windows, but nonetheless it has to be Windows operating system. In other words, it doesn't run well in Linux because it doesn't know how to ask Linux for the same resources. Okay, so here's the question. For class purposes, I made a copy of the CD, and I have to return the CD to the person who loaned me the CD. So it's in this folder here. And I'm not sure how well, I guess you can see it. This is the executable. But normally, an executable designed for Windows doesn't run in any other operating system, not Mac OS X, not Linux, unless there's a technology to help it. In other words, if I try to run it here, oops, it complains and say, no, cannot execute this binary file. I don't recognize this as an application designed for Linux. So what I'm going to do here is I'm going to say, yeah, that's wine. What wine stands for is wine is not an emulator, but it really is kind of an emulator of sorts. So when I run this, it'll take a little bit of time to start it up. It gives me a lot of potential error messages, but it will run. It's just saying that certain surfaces of the quote-unquote government is no longer accessible. but nonetheless, it runs well enough that we see it. Okay, more or less. Enough for this class. So what is happening here? I have an application that was designed for Windows, and I'm running Linux here. So what is going on here? What do you think Wine is doing?
Translating.
It's translating, exactly. That's the best way to, or emulating, okay? It's translating / emulating. In other words, we have an agent here to help out, people. We have an agent, let's say we have a British native who just, came to the United States and doesn't know, okay, but where do I go to report a car accident? What do I do to get my driver's license? Where do I go to blah, 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 okay? So for a fee, okay, in this case it's, efficiency and execution time. For a fee, Wine is an agent. Is an agent native to Linux. Is an agent native to the American government. However, this person also knows the British system well enough and say, oh, you want to get a driver's license? I can show you where to go. Here's the DMV. You want to get what are the resources? Oh, you want to report an accident? Okay, you want to go to the local police station, and I can show you where you can go. To the closest sheriff's police station or the sheriff's how do you call those, headquarters? Substation, okay. But we have a translator. And that's why I can run an application that was intended for Windows, but in Linux. Okay. Are there any questions about this kind of technology? So this is just an introduction, but I want to talk about it because I'm using it. So this is the best way to demonstrate and explain the concept because we are using it in the class. Let's go ahead and go to chapter 2 because we were already talking about chapter 2. And let's see, let me try to recall where we were last time. I think we were talking about storage devices at least. No, not yet. I think we kind of jumped around, didn't we?
We just finished up the personal computer basic stuff.
Okay. So let's go to processor, microprocessor basics. I was talking about the textbook for this class the other day, and then one professor who I will not name said, well, if you want to turn people away from computer science, this is the best book to do it. Because it is a little bit too in-depth when it is not called for, okay? So I'm going to skip, some of this stuff here. And I'll just talk about what a processor is. Now, this is really good stuff, especially, what is on this side here. Modern processors and whatnot. And this is why they can have, one edition per year, because Intel releases, new versions of their processors every year, okay? And that's how they can stay current and say, and guess what? This is a new edition of the textbook, and you have to buy it. So there's no way you can sell, sorry?
They just try to make money.
Exactly.
Books.
Exactly, because otherwise they can just put a link here to Intel's website. Then you can read all about the processors at the Intel's website, right? I mean, there's no need to do it here.
It's like a list this long.
This is a list that long, or you can point it to Wikipedia.
Yeah.
Yep. All right. So what is inside the processor? I don't want to talk about anything that is too specific. Well, what is inside the processor is, okay, let's look at the processor as a whole first, okay? What is that one chip, it's about yay big that you put onto the motherboard inside the computer, and that's your processor. What does it do? It processes, right? So from the outside, what it does, what do you think what is its function? It has to interface with stuff, right? I mean, just the processor by itself is not very useful.
It's like a pass-through almost. This information goes to the processor to the RAM and back.
It passes through, but also with processing. Okay. So if you think about the process, I'm just going to draw a picture here. It's all kind of like a condensed version of the textbook. Okay, if you have a processor, let's say we represent a processor like this, almost everything inside the computer has to go through the processor. Not exactly everything, but most. Okay, so on one hand, you have random access memory. For the most part, if you think about random access memory, you can just look at it as a really thick notebook that is erasable. Okay, so you can put content onto the pages, but also you can erase it and put something else. You can overwrite the content on those pages, and that's random access memory. You also have, a little bit of ROM, read-only memory. And the textbook talks about all kinds of different types of ROMs, but they're all about the same. They're all read-only. And that gives your computer the ability to at least bootstrap. In other words, it gives the minimal instruction to the computer and say, okay, when you wake up, look onto the CD drive, look at the hard drive to look for a boot sector, and then from the boot sector, execute that code and try to look for the actual operating system. So that's what the ROM is, because without the ROM and with only RAM, your processor doesn't know, okay, how do I get started? I don't know. Yep, good question. Yeah, the processor would just say, good question. I'll just turn myself into a big heater. But not so much anymore. I think the best heater was the Pentium 4 processor. It was the best ever. It executes, it has the least processing power per watt. That turns it into a very good heater.
TDP on the new is like 95 watts now.
Yep. So these two will interface with the memory, and they're both memory types. So this thing here, this connector, connecting both types of memory to the processor, is called a memory bus. Okay? I don't know why they use the term bus to represent the connection between components, but it's more than one single wire, that's for sure. Okay? What else do you think you will feed into the processor? Okay, so I'll just say that this is our processor here. What other components do you specify when you purchase a new computer or when you put a computer together?
Your hard drive.
Your hard drive, okay. Now hard drive is a little bit different. The hard drive goes through another thing first before it goes into the processor. So this is our hard drive. It goes to a hard drive controller. In this case, SATA is the current one, but in the good old days we have IDE, Enhanced IDE, and then before that we have what? SCSI, and then at the same time with SCSI we have another standard. I can't remember those names.
Solid state.
No, solid state is SATA. You talk to solid state would go through a SATA controller too. So if you have a solid state drive, it goes to the SATA drive.
CPI.
In the really good old days, we have different ways, like the MFM, I think.
Well, I mean, I'm talking about new solid state drives don't go through SATA controller.
Oh, they don't?
No, it goes through. It uses a SATA connection, but the system manages it within the SCPI controller.
Ah.
Because that's how you can use trim functions on a solid state.
Okay.
So.
But some can still go through SATA.
Yeah.
So in terms of drawing the picture, this is
Yeah.
how it's connected. What else do you need when you use a computer?
Video card.
A video card is good. Okay, so we'll talk about the video card. But once again, the video card does not go to the processor directly. It goes through first. It goes through what they call a PCI Express controller, or the bridge, and then from that you can go to your NVIDIA graphics card or whatever graphics card you want to put into the system. Depending on the processor, sometimes that's also not the case. Like with the i3 and the i5 processor, the graphics chipset is actually inside the processor itself, which is a strength and also a weakness at the same time, depending on your perspective. If you are a super gamer, it's not really sufficient because the one built into the processor doesn't have the performance to run high-end games. But on the other hand, if you just want to reduce the cost of your computer, and the worst you can do to, in terms of video demand, is to play YouTube or your Blu-ray, the video chipset inside the processor is already sufficient. So this is actually, talking about a system that has, a higher performance type of architecture. What else? We're talking about, SATA, which is a really high speed device. IDE Express is also potentially high speed.
USB,
USB, very good. But what do you hook up to USB?
mouse, keyboard.
Just about everything else, right? Everything that is slow, you can go through USB. So USB goes through a big, long list, like a keyboard, mouse, game controller.
External memory.
Hmm?
External memory.
External memory. You mean thumb drives?
Yeah.
Okay, thumb drive. What else? Sound cards, even. Network cards. Or dongles, because that's how we call those. Bluetooth, and so on. The list just keeps going and going. Scanners, dumb terminals, modems, lots and lots of devices you can hook up
More
to the USB
ports.
side. Hmm?
More USB ports.
Yes, hubs, USB hubs to multiply. Yep, okay. What else? Am I missing anything here with the processor? I think I got all the major components. Okay, all the major components are here.
Power.
Sorry?
Power. It all needs power.
Yeah, power, but in terms of functionality, this is pretty much how it is used, how it's hooked up. These two or several other components, sometimes we kind of combine these and call it, a particular name. It's called the North Bridge, which is really just a technical term to talk about, a subcomponent inside your system that has to handle high-speed devices. Your hard drive is considered a high-speed device, and the graphics card is definitely a high-speed device. On this side, some motherboards may have a sound card built into it. Sound card, you might have a NIC built into it. This is called, guess what? South Bridge, exactly. Okay, so you have a processor, North Bridge, South Bridge, and modern processors do not go through the North Bridge to talk to memory anymore, so memory is direct. What does the processor do? If you just think about this, okay? Think about what I'm doing right now. Okay, I'm moving my mouse and the cursor moves on the screen. It's just that. How many of these components are involved in this process? Well, let's think about it. Let's start with moving the mouse, okay? What is the mouse?
USB.
It's an input device. So it goes from here, goes through USB, and then the processor cannot just say, hey, USB, you got something for me. Because the processor needs instructions, right? Where do you think the instructions come from? It comes from memory. For the most part, it comes from RAM. Okay, it does have instruction in ROM, but for the most part, when the computer is actually loaded up like this, the instructions will come from RAM. So it accesses RAM to think about, okay, what should I do about the USB thing? It executes the function, which has a lot to do with the operating system and also the graphical user interface, and then it decides, okay, I need to update that little pointer thingy on the screen. Then what does it do? The processor now has to talk to the North Bridge, which contains the PCIe controller, a PCI Express controller, and then talks to the graphics card to update the appearance, where the mouse pointer is on screen. So for little things, even that, it involves a lot of the components. What if I decide to save a file? If I save a file, it will also have to talk to the SATA controller because you have to store it most likely onto the hard drive or the solid state drive, or talk to the USB to store onto a thumb drive. So almost everything has to go through the processor. But remember what I said, not everything has to go through the processor, it's just most of the things has to go through the processor. What do you think sometimes doesn't go through the processor itself? Any idea?
Saving memory on the hard drive.
Saving memory on the hard drive is a good one, okay? When do you want to save a massive amount of memory onto the hard drive? Hibernate. When you're, sorry, go ahead.
Loading an application.
Loading an application actually does have to go through the processor because it has to read the application and put it at the right place. But when you're hibernating, where your processor or when your computer is saving the entire state of the system, for the most part, it's just dumping whatever is in RAM onto your hard drive. So for that operation to happen, going through the processor all the time really doesn't help, and it's kind of slow to do it that way. So this part is kind of optional because I think it's a little bit beyond the scope of this class. But sometimes you can bypass the processor and have a path to go like this instead. It has a name. It's called DMA. It's called Direct Memory Access. Okay? How many people still remember the DMA setting on old extended IDE controllers? No one? Okay, you guys are. Yeah, that's a really old type of system. D or Ultra DMA when it became faster. But this is a good kind of a schematic picture of how everything is connected. That's from the outside view of a processor, okay? Because I'm only looking at the processor as a little box. Now, the book does talk about the processor from the inside. In other words, what is exactly inside the processor? Well, I'll just kind of finish up this page here, which talks about random access memory. Assuming you have already read the textbook, this is pretty much old stuff. The question is, how much memory do you actually need in order to run your system efficiently? It all depends on what you're doing with your computer. Like right now, with teaching this class with a recorder, a browser, and also this application running, I can show you exactly how much memory is in use at this point. Let me see what is the best way to do it. I did not install the application that gives me a very easy way to see it. I can always do it like this. In Linux, there's a command called top, and it shows you all the vitals of the system. So this is telling me all the vital stuff. It's telling me the load average is close to 1, which is not bad at all, because if this thing has 4 quote-unquote processors, because it has 2 cores and it has hyper-threading, so technically it has 4 cores, or it can be seen to have 4 cores. The system load is actually pretty low. I mean, it's only using less than 1/4 of the resources. It's telling me that it has this many kilobytes of memory. So it has about 4 gigs of memory accessible, and 2 gigs are in use. But you know what? Out of the 2 gigs, about 1.5 gigs are used as cache. So the operating system is only using less than 500 megabytes of RAM at this point, which is not bad at all, right? It's only using 1/8 of the available RAM at this point. What type of application do you think will consume a lot of RAM? In other words, you want to put in more RAM into your computer if you want to run this kind of applications. What kind of applications?
Photo editing software.
Sorry?
Photo editing software.
Photo editing software, unless you're talking about the GIMP.
Yeah.
If you use the GIMP, you only need you don't need that much memory, unless you have to you want to back up a lot of steps. You still need it in that case. It also depends on the size of the photos that you're editing. If you're editing only for web purposes, which means your pictures are not going to be very high resolution, you'll still get by with less memory. But on the other hand, if you're editing 18 megapixel pictures, and you want to be able to undo every single step, and you're basically just doing all sorts of steps and processing on the picture, it does take up a lot of RAM, because every time you do something to a digital picture, it actually stores the version of the picture before you do something to it, so it can be undone. Okay, what other application or what other types of program require a lot of RAM?
Video editing software.
Sorry?
Video editing software.
Video editing, say photo editing, video editing, anything else? Games, okay? Why do you think games consume so much RAM?
Because things are always changing on the screen.
That's handled mostly by the video processor. It's using RAM to do a few things. One is to buffer up frames, okay? Because if you only want to draw the current frame at a time, it can only do so much, at a time. But if you can buffer up at least a few frames, that means when the processor and the video card has time, it can pre-process and say, okay, I know the next 2 or 3 frames would be these, and it can do it ahead of time. It also uses RAM to store the games, okay, data information that is specific to the game. Do you guys still remember in the good old days when you actually have to put in a DVD-ROM or CD-ROM to play a game? because the cutscenes and all the data will still need to be loaded from the CD-ROM. What was the experience? Between scenes, they try to make the cutscenes more enjoyable. Why?
From now until then. From now until
Because it takes a long time to load up, the next, part of the game. So they have cutscenes. If you play StarCraft, there are a lot of cutscenes. And for the most part, they're fairly entertaining. But the cutscenes are there to keep you occupied when the game is loading up the data, the maps and whatnot for the next stage. If you have a lot of RAM, you can preload a lot of stuff ahead of time, so that your gaming experience will be more seamless. Yep.
But nowadays, video cards having their own set of RAM,
Mm-hmm.
they buffer inside the video card itself. It
Correct.
doesn't actually go to the computer's memory. It stays unless there's an overflow.
Unless you have a $30 video card.
Yes.
Yeah. Then it chews up system memory because the graphics card itself doesn't have a lot of RAM. So a lot of times when it needs to store and buffer up, frames, it's using up system resources for that. Okay. Anything else that require a lot of RAM? Yep. Go ahead.
Running any type of virtual device, such as the emulator.
Exactly. Why does it use up that much? Because it's not a 100% full up emulator. But if you use any type of emulator, a real emulator, it does consume a lot of RAM. But for the most part, for different types of applications, they don't really use a lot of RAM. But Windows itself uses up how much RAM?
I
Half a
don't.
gig.
Windows 7. Let's just say it's Windows 7
Two.
Home.
Home uses like 1 to 2.
1 point something.
Yeah.
Yeah. But if you don't have 2 gigs of physical RAM, it has problems.
Aging file.
Hmm?
Aging file.
All right. So that's basically all I want to talk about. RAM. How it works exactly. It's not as important. So we'll move on. It talks about how much RAM you need. And today's personal computer typically features 2 to 8 gigs of RAM. For good performance, running Windows, you need at least 1 gig of RAM. That's actually not a true statement. You need at least 2. If you only intend to run Windows 7 on its own and just use Notepad to write something, yeah, 1 gig probably will be sufficient. But if you want to do something, like use Microsoft Office or any type of real application, you need 2 gigs of RAM. Okay, here's another question. Look at this picture here. What if you don't have enough RAM? What if you're using a heavy-duty program that needs a lot of RAM, but you only have 2 gigs installed?
Yeah, fine.
Sorry?
It said it uses your hard drive.
It uses your hard drive. That's exactly right. Because what happens is when you don't have enough RAM, physical actual RAM, the system will try to juggle things. It's going to do something like this. Oh, you know what? This part of memory you have not accessed for a while, but I need some extra RAM right now. So what I'll do is I'm going to go to RAM, okay, and I'm going to see which part of RAM has not been used for a long time. It's like, okay, I don't think we need it right away. I'll put that stuff onto the hard drive to free up some space in RAM to put something that has to be in RAM right now because I need access to it right now. Okay? So that means it's going to use up hard drive resources. You will need to move stuff from RAM onto the hard drive. What if later on you need that stuff back? You need to reverse the operation. Whatever is taking that spot in RAM, it has to be first saved onto the hard drive, and then you can go to the hard drive to restore whatever was stored earlier back into RAM. So you're basically always juggling resources because there's not enough RAM. Okay? And what is the user experience? What do you see from your perspective as a user? One thing, you see the hard drive blinking all the time. Sometimes it's continuously lit, right? How come that hard drive light is almost like a power light? It's always on, right?
Slower experience.
And it's extremely slow. Okay, why is it so slow? I mean, didn't we say that the SATA controller is a high-speed device? I mean,
The processor still has to interface between something and the hard drive.
true, But that's not even the reason why it's so slow. Let's think about how we quantify the speed of memory. Okay, how do we specify the speed of memory? I don't need the actual technicality of DDR2 versus DDR3. So let's say it's DDR3. How do we rate? How do we quantify the performance of memory? Okay, and what is the current top of the line megahertz or clock speed?
3.67, something like
Okay, you mean the actual number of the unit?
that. 2.67 gigahertz, I think.
Gigahertz. Okay, and the memory path is how wide? How many bits can I transfer at a time? 128 bits, 64 bits, 256 bits. What is the width of memory path?
You're talking about like the actual speed of the RAM itself and not the processor? Or
Not the processor, just the width of the path.
The highest I've seen is 2,004 megahertz for RAM speed. That's the front side bus. And then the highest bit rate is 512 size bit rates.
Okay, 512, and then the unit is what? 512 bits? Okay, so we're talking about this number here. All right, so if you guys have read the textbook, you know what is a hertz. A hertz means ones per second. A giga means a billion. So this means 2.67 million times per second. That means I can transfer 512 bits, and you divide it by 8 to get the number of bytes. I can transfer that much information 2.67 billion times per second. That's a lot, okay? That's a lot of stuff. What about the hard drive? If you go to Fry's right now and say, I have money, I can buy the highest performance hard drive that Fry sells. What is the RPM rating on that drive? What is the revolution per second rating on that drive? 10,000? 75? Let's say they have 10,000, okay, 10,000 RPM hard drives. 10,000 RPM, okay, which is awfully fast. Okay, these are usually reserved only for servers and really critical applications. Most consumer hard drives will spin at 7,200 RPM, and on notebook computers, it's even more common to find 5,400 RPM hard drives because they save power. Okay. How many times do you think this is turning per second? I need a calculator for that.
60,000.
Divided by 60, right?
Times
Okay, I just need a approximation. For this class, approximation of 50 equals 60 is good enough. So we have 200, right? Is my math right here? Yep. Okay. So we have 200 revolutions per second in this case. Now the wait, sorry?
Let's see. Times that by 4.
No, this is memory. This is how fast memory can transfer, and this is how fast the hard drive is spinning in this case. Now, how do you organize, or how does the computer organize data on a hard drive? Okay, a hard drive has multiple platters. Each platter is just a disk with a very smooth surface with magnetic media on it. And then all the platters will be connected by a spindle, and then the spindle rotates, so therefore the disks will be rotating as well. On the disk, if you just put a disk head at a fixed position, it will be able to read what we call a track. In other words, one concentric circle on a surface is called a track. On the track, it is further divided into sectors. Okay? Sectors are basically just portions of a track. Even assuming that your eSATA or your SATA controller can be infinitely fast, it can keep up with memory any day, any time, you have a problem here. The disk head is fixed here. What if the sector that you want to read is all the way over here at the other side of the disk head? What do you need to do? What do you need to wait for?
It to rotate.
It has to rotate, right? So the hard drive has to rotate to the right place before the disk head can read the sector that you want to read. How much time will it take in this case? We have a high performance hard drive here. It is rotating at 200 revolutions per second. 200 revolutions per second is the same as how many hertz? How many times per second? It's just 200 hertz, right? And with 200 hertz, what is the time that it takes for one full revolution? It's 1 second divided by 200. So the rotational delay for one full revolution is 50 milliseconds. But on the average, it's only 1/2 of that. Okay? So the average is only 25 milliseconds. 25 milliseconds doesn't really sound too bad, does it? I think I got the math wrong. Excuse me. I got one. It's off by 1 order of magnitude. But for the purpose of this discussion, it really doesn't matter that much.
How
Yep.
do these sectors go bad?
Then your operating system has a way to mark a sector as a bad sector and not use it.
How do they go bad?
How do they go bad? It's just imperfection on the surface. A lot of things can go wrong. Your hard drive controller actually has a built-in ability to detect that sort of thing and basically detect and say, okay, this sector is not usable anymore, and it will just use another sector. In other words, what you tell it to use is not actually translated to the physical actual sector. It has an internal management system to handle everything by itself. Okay, 2.5 milliseconds. 2.5 milliseconds is not a whole lot of time, is it? It's basically equivalent to 400 times per second. How does that compare to this number here? Okay, so this is 400 hertz. So how does 400 compare to 2.67 billion?
It's really close.
Not even close. Let's just talk about the order of magnitude. This is in the order of hundreds. This is in the order of billions. Hundreds versus billions. How many zeros are we talking about? One has 9 zeros, one has 2, so we're talking about 7 zeros. We're talking about 10 million times in terms of just the sheer difference of order of magnitude. I don't really care about the 4 here. For all I care, this can be 1, can be 9, can be 6, doesn't matter. I'm just talking about the number of zeros. It's off by 7, 10 million times. So what does that mean? That means you can have the most powerful processor on the planet. You can have the fastest RAM you can possibly buy, but not a whole lot. You can have the super fast SATA controller and a hard drive to go with that speed, and it will still be very slow because you have to constantly swap things around. So that's why in some cases, if your applications require a lot of RAM, like doing video editing, photo editing, games and stuff like that, don't buy a more powerful processor, because if you buy a more powerful processor in this time, what is it doing most of the time when you have to swap things around between RAM and hard drive the whole time? It's doing this. Your processor is going like, I'm just waiting for the next page to be loaded. And then do some more of that. Yeah, I can see you're clicking the link a few more times, but sorry, I can't really do a single thing right now. Go back to twiddling the thumbs. Oh yeah, the hard drive has another page loaded. Great. Okay, let me tell you. Now load up the next page because I can't execute it just yet. That's what it's doing. Okay, you can have the best processor, the best i7 processor from Intel. But if you don't have enough RAM to keep the processor busy all the time, your system has really, really bad performance. Okay? So I wouldn't spend too much money on the processor until everything else is ready for execution, to have high efficiency in terms of execution. RAM isn't all that expensive anymore. Yep, it's relatively inexpensive compared to upgrading to the next level of a processor. So look at your application, what you're doing with your computer, before you decide what you need to upgrade first. What about upgrading this hard drive? Let's say somebody came up with a 15,000 RPM hard drive. Would it help a lot? No, because it still has a rotational delay at about the same order of magnitude. If you upgrade your RAM, you'll be changing the order of magnitude. You're not changing this number. You're not changing 46. You're changing that 7 zeros. You're getting rid of the 7 zeros in terms of delays. So are we doing okay so far with this discussion here? Is it relating to what you guys do, with your computers, and you might need to think about when you upgrade or buy your new computer, next computer? Or you can switch to Linux. You can dual boot. There are ways to use Linux without. Okay, and then it talks about read-only memory and double EEPROM. Yep.
Is it possible to dual boot a solid-state drive, or would that not be a good idea?
I think you can dual boot. That's a function of the BIOS, which is, well, guess what? What this page is about. The BIOS, which has a new name, I cannot remember what the new name is, but it's basically bootstrap instruction for the computer. So when I first start up this computer, it has some basic instructions that has to be there to execute first. And that's basically your quote-unquote BIOS. BIOS stands for Basic Input-Output System. And it just does some really simple things. But what we think is a simple thing is actually not that simple. Because one of the things your system has to do is to figure out how much RAM there is in the system first. How do you know how much RAM there is in the system? BIOS has to test it, okay? But how does it test how much memory there is in the system? You're basically holding a notebook, a writing pad, and you don't know how many pages there are in the writing pad.
It goes through everything.
You basically have to write to a page, and then you test, do I see this page again after 100, after 200, after 400, after 800 pages? Because what happens is, if you have 1 gig of RAM, now this is obviously very simplified. If you only have 1 gig of RAM, when you access location 0 and write a certain content to location 0, that content will appear again at 1 billion. And it will appear again at 2 billion. It will appear again at 3 billion, and so on. In other words, it will repeat itself depending on what is the actual amount of RAM installed in your system. And that's what your BIOS is testing when it first starts up, is to basically check how much memory is actually installed in the system. What else do you think your BIOS will do? And sometimes if you configure your BIOS incorrectly, things can go really bad. And it relates to RAM. Has anyone heard of the term called wait state, or CAS? When you specify memory, when you specify the speed, in addition to just the frequency, sometimes they also tell you the delays or the wait states that is needed. If you configure that part wrong, you can render your computer not very usable, because it will try to access memory either too fast, and it will be marginal. The worst case is it's marginal. Okay. When your room is at 72 degrees Fahrenheit, it works correctly. You bump the temperature up by 1 degree and it stops working, sometimes. So this part talks about all these different type of technology. Double EEPROM. Quick, what is the full name of a double EEPROM?
Electrically erasable program read-only memory.
Yes. So that tells you that it has a long history. Okay, this is how your computer terms come about. Is they start with something simple. Okay, so I'll just go ahead and use it. Well, I can use my notepad to talk about that. In this part, you don't have to remember. I just want to give you a little background of these terms. Okay, EEPROM. The M stands for memory. Okay. And within memory, we have random access, which means it is easily erasable. And we have read-only, which means it is not easily erasable. For the most part, it is intended only for read-only purposes. And then we have PROM, which means it's programmable read-only memory. How does that work? Okay, in the really good old days, like 30 years ago, people actually had ROM. PROM, excuse me, they had PROM. So how do you think PROMs work? You buy these chips, okay, they're about this size, okay? You put it into a special PROM programmer, and then you use a special program to program it. But as PROM, without the EE, what if you decide, oh, I just put the wrong content onto this chip here? What do?
Chip's dead.
You chuck it, you toss it into the waste bin, and this is before Cal EPA became conscientious about this sort of thing, so it all goes to the trash can. Okay, and then you need another one. You need a fresh PROM that is blank to reprogram. PROMs work by a very non-reversible way. In other words, when you have a fresh PROM, it has quote-unquote a lot of fuses. Okay, every bit has a fuse. Okay, every binary digit has a fuse. So the way you quote-unquote program it is by breaking the fuses. So I'm just making an assumption here. With the fuse present, is representing 1. If the fuse is gone, it is representing 0. So you basically look at the memory that you want to program into the PROM, and then you figure out what fuses has to be blown. But after a fuse is blown, can you replace that fuse? Nope. And that's why it's called PROM and not EEPROM. Later on, we had EEPROMs, which are really kind of, at the time, it was a big step forward. EEPROMs are about the same size. They typically come in packages about this size. And it is programmable because it has the P in it, but it's also erasable. And how do you think we erase EEPROMs? Ultraviolet. It's ultraviolet. So you have a choice. Okay, if you program an EEPROM incorrectly or you need to update it, you have two choices. This is back when these are the chips with a little window, a transparent window in the middle of the entire chip. Have you guys seen that stuff?
I think so.
Okay, some of you might have seen that. Okay, so you basically peel the label off, so you expose the window, and then you can either leave it in the sun for a few days, or you can put it into a EEPROM eraser, which is just a UV source, and then you can usually do it in about 15 minutes. Okay, and that's how you erase a EEPROM. It can only go through a few hundreds of cycles before it cannot take on the new program anymore, but that's how it works. And later on, we have electrically erasable, programmable, read-only memory, which is what is on your BIOS or on the motherboard these days. And that means you don't need a source of UV to erase it anymore. Okay. Any questions about this? Just the long history of how the term EEPROM comes along, or double EEPROMs, as some people call that. How many people have upgraded your BIOS? Okay. And typically, it's relatively safe to do that. I think the BIOS has a part that is not erasable at all. So it can always go back to that one state and start from there again. So this is basically your BIOS configuration screen. It allows you to specify a few things. When your system starts up, it can change performance, your boot order. In other words, when your computer starts up, where does it look for the operating system? Most of it would just say, go to the hard drive, because that's where the operating system is installed. But sometimes you might want to boot from a CD-ROM or a USB thumb drive. Why do you want to boot from a CD-ROM or a USB thumb drive?
Well, if you're installing an operating system, that's how you can install it onto the hard drive.
Or if you don't like the operating system already installed on a machine that you have no control over, yep, just like in this case, I'm running this entire thing from a thumb drive. It can also run from a DVD drive if I want to. Okay. What about the situation when your Windows system is infected? So to the point that it cannot even boot. What do you do? You can't even get to safe mode. It is possible to host it to the point where you cannot even get to safe mode.
Depending on how your BIOS is configured, you probably have to go into BIOS and instruct it to boot from wherever the source is. So
correct. You can manually trigger the boot menu. Then you can select where to boot from. But nonetheless, the point is, if the operating system on the hard drive is corrupted or infected to the point that it cannot even start up, or you cannot trust it, then you have to start an operating system from another source. And that's why you have to be able to get into the BIOS screen and convince your computer and say, don't start from the hard drive, because that's either a host operating system or cannot be trusted. Okay? And then you can start another operating system from a CD-ROM drive, DVD drive if you will, a thumb drive, or some sort of external device, so that you can start to rescue the operating system that is already installed on the hard drive. This is also a good place to talk about a rootkit. What is a rootkit? Just ask Sony. Sony is really good at that sort of thing. Some people know or remember, Sony and the whole concept of rootkits. Okay, you guys know what a virus is, right? In general, a virus is basically malicious software, malware, that has the ability to spread. Once you invite it into your system and you trigger it, then it can send itself to other people. That's what a virus is. So a virus is for the most part passive, okay, until you click on something. Then it activates its code and then it starts to do malicious stuff. What is a worm in computer terms?
It's a whole system. Doesn't it bypasses?
It's active. Okay, the difference between a worm and a virus is a worm is active. In other words, it's a program that runs on its own and it seeks out its next victim actively. Okay, and then it infects the victim system and then replicates itself over there, and then it becomes active again. No action is required on your part. That's a worm. What is a rootkit?
It roots itself into a normal program.
A rootkit, as the name implies, goes really deep into your system, and that's why it's called a rootkit. Or the term might have come from the Unix/Linux world, where root is the administrator. A rootkit is particularly nasty. It can be planted by a virus or a worm. So a rootkit is basically what is installed on your system. It is very deep within your operating system. In other words, think of it this way. You have a member or members of a mafia organization working in the government. Okay? So now the rootkit, compared to other malicious software, has some special abilities. Okay? When we're talking about just normal viruses, you can run a virus scanner. Okay? So in the analogy of society, a virus scanner is the police, right? And they're just patrolling the area, looking for suspicious people, stop those people, throw them into jail, quarantine, or just erase those files altogether. Okay, so that's your typical run-of-the-mill virus where you can stop them by a virus scanner. A rootkit is particularly insidious because it is planting itself inside the operating system. In other words, it can hide processes, okay, and files and other resources from a virus scanner. Or itself can also be directing your operating system to do really bad things. How many people have watched Star Wars episodes 1, 2, and 3? Think of the Emperor. Okay, and your operating system is the old Republic. Okay, that's a rootkit right there. It plants itself right into the operating system, and therefore there's no way to get rid of it easily. Yep.
So what is a Trojan?
A Trojan is just an approach. It's basically, it describes how a particular malicious piece of software can get into your system. So a Trojan is basically by invitation, and it pretends to be something other than itself. In other words, it doesn't say, hey, I'm a virus here, download me and install me. It pretends to be what? PowerPoint presentations. Hey, click this link, it's a really fun presentation about kitties or whatever. Or drivers, or documents, Word documents, Excel documents, they can all contain viruses, but they usually pretend to be something else so that you invite it into the system and then it can run. Okay? Most operating systems will give you a chance to stop it first, but a lot of users will say, but I really want to watch that presentation, and click yes, run, and that's how the virus can run in that case. So Trojan describes a vector or a way to get into a system. A worm is not a Trojan because it doesn't need invitation. It can dig a tunnel around the obstacle by itself. So when you have a rootkit installed in the system, what are you going to do? First of all, how can you even tell there's a rootkit installed in the system? Well, I'll just run a rootkit scanner, right? But a rootkit scanner is not going to help you because when you run a rootkit scanner, it still relies on system resources, right? Okay, show me all the files in this folder. What if the rootkit is already installed in the system? It can decide, hey, you know what? These files I don't want you to see at all. So when you type dir or when you double click on a folder, it doesn't show specific files. So how can your scanner look for that? Yep.
There are some programs out there that you can boot up outside the OS.
Yep, you have to boot outside of the OS to do it.
When you boot up, you can put it in your your flash drive or your CD-ROM drive and boot it up, and it'll actually the operating system isn't functioning at that point, so nothing can be hidden. It'll just scan that.
Yep, and that's why you need to boot from. You need to be able to boot from USB or a DVD drive, so that you can at least assume that whatever you're running is not infected itself, and therefore you have a better chance of locating malicious software. Are there any questions at this point about why you might need to change your BIOS settings sometimes? Okay. I know I'm digressing a lot in this class, because a lot of times, it's not just talking about what it is, but why do you need access to it? Why do you need to change it? And why is it even in your computer? Okay, storage devices, once again, there's a lot of classifications here. For the most part, you just have to remember, there's magnetic, solid state, and optical. Optical is really only there so that we can, record stuff for compatibility issues, mostly. Why do you want to burn a DVD these days? A video DVD, not a data DVD. So that grandma who doesn't have a computer, who only has a DVD player, can watch your videos, right? But amongst yourselves, okay, your peers, what do you use to distribute media? It's like, oh look, this is the recording of my friend, doing bungee jumping.
Facebook or YouTube.
Yeah, you don't even distribute media, right? You just tell your friend, look up my channel on YouTube, and it is already uploaded there. Just like the video recording of this class, it's already up there on YouTube, and there's no need to burn DVDs. What about your cars? Okay, you like to listen to music in your car. Do you still use optical disc in a car these days?
No.
Why not?
Just skipping.
It's skipping. It can skip depending on how you drive.
Some people, or some
In your suspension, yes. Go ahead. Sorry.
some vehicles you can plug in USB or red and the audio, left and right audio jacks.
Okay, that's another way. Yep.
More and more often, car manufacturers aren't producing cars with them anymore because it's cheaper.
It's exactly. Think of all the hardware on an optical drive. It needs a spindle. It needs to spin the disc. It needs a head to pick it up. And in that case, you need a laser. There's a laser diode to basically shine a very small amount of laser light onto the disc so it can pick up whether there are holes or not. There's a lens system involved, both for projecting and also picking up the return. It's really high precision too, because if you knock an optical drive around, sometimes it will lose the tracking, and it has to go seek again and reestablish the tracking. And it's also very slow. Okay, has anyone tried to change tracks randomly on a regular CD, music CD? It's kind of slow, isn't it? That's because the entire CD is one single track. Okay, so what do we do with cars these days? Okay, you mentioned audio in or USB jack, but even that I would consider kind of old school already. What do we do these days? Bluetooth, yeah, exactly. Just Bluetooth it. You can Bluetooth stream it from your phone, stream it from your iPad. You can stream it from anything that is Bluetooth capable. It's a very smart move on the manufacturer's part. Why? How expensive do you think is a little Bluetooth dongle that hooks up, to the audio circuits? Next to nothing. Okay, and what about the expandability of that approach? Lots, right? I mean, once you have Bluetooth connectivity, the player is no longer on Honda's or Toyota's or Ford's part. It's on your part, right? So, are you happier that now you have to pay your own player? Yes, absolutely. Because now you can upgrade your phone to have a better phone next time, and it can play your music even better. It maybe has a better way to shuffle it. Maybe you can even stream directly from your home computer. Right? If you have an unlimited data plan, you can do it. And Bluetooth is also becoming more and more useful for cars because they can also use Bluetooth and connect it to the OB, onboard diagnostic, OBD2 circuit of a car. So if your car has a check engine light on, okay, your car can even kind of broadcast it using Bluetooth and say, okay, my check engine light is already on, there's some problems. So when you drive into a garage, if the garage is set up correctly, they can tell that, oh, okay, your car has a problem. I think your knock sensor is not working correctly anymore. All without opening the hood or even getting into the passenger compartment of your car. I'm not quite sure whether that technology is enabled or not, but I think it is possible. There might be privacy issues, that prevents, people from, doing that by default. But it's all getting there. But having a Bluetooth interface is also bad in a way. Why is it bad?
Because it's less secure.
It's less secure, exactly.
It's only the password you get into a Bluetooth is usually a PIN, which is 4 to 6 digits.
Exactly. And how far can someone try to hack into your Bluetooth system? We talked about that a little bit on last Thursday, outside of the classroom. Has anyone heard of the term called Bluetooth or Wi-Fi sniping? Okay.
2 miles away.
It depends on how good your antenna is. Okay. The thing about this is, most people think, you can receive, you can eavesdrop, but you cannot transmit. But that's not true, because if you have an antenna, let's say has 50 decibel of amplification, it's amplifying both ways. It's amplifying things coming in. It's also amplifying things that are going out. So the 2 miles will be applicable to both in and out. So if you think about it this way, someone with the proper hardware and also the proper software can potentially hack into a Bluetooth connected system from 2 miles away, and that's a long way. Okay, 2 miles is a long way. Yep.
I've put a stereo with Bluetooth in my car, and I can probably be about 500 to 600 feet away, and my phone will pick up the Bluetooth in my car.
Which is annoying, isn't it?
Yes. Like walking through the house and like you turn your car on to heat it up like when it's cold,
Yeah.
and then your phone starts ringing, and then it picks it up in the car, and you have to go out to the car to answer the damn call.
Now you need an app that will look at your GPS position, the Wi-Fi signal strength, and whatnot to determine, are you really that close to the car when it needs to, when it can actually use the car's own Bluetooth? I'm sure you can write an app like that. I have a class coming to tell people how to write Android apps, so that's cool. All right, we are running out of time today, so go ahead and read ahead of me, and then we'll continue these discussions on Thursday.
Did you get my
Yes, I got it filled in.
We have to stop your recording.
Oh, yes, I need to do that. Is that the one? Fill it?
On the mood?
Yep.
On mood?
Yes.
Or, do you have any assignments posted up yet? Because mine wasn't showing any assignments.
On Blue? Yes, on